So we are studying the hydrogen atom, and in the hydrogen atom, we actually have not one body problem, but two body problem. And in the two body problem, we need to have coordinates of each body, like R1 and R2. R1 is the proton coordinate, R2 is electron coordinates, and total Hamiltonian is sum of proton-electron terms. And you can see the interaction between proton and neutron only depends on the distance between them, R1 and R1 minus R2. Okay. Here, I was thinking them to be equal mass. If they are equal mass, center of mass is going to be R1 plus R2 over 2. But since they are not equal mass, we need to do M1 R1 plus M2 R2 divided by M1 plus M2. I think somebody was pointing that out. And the relative coordinate is relative coordinate. And the problem is to change the variables from R1, R2 to uppercase R and R without subscript. And you can see, so there is like a piece that only depends on little r, and there is also a piece that only depends on uppercase R. That means the Hamiltonian is separable. If Hamiltonian is separable, we can try a separable ansatz, exactly like we did for many other problems, and we can separate R equation, uppercase R equation from lowercase r equation. Okay? And in that case, lowercase r equation becomes a single electron in a central potential. With the difference, m here should be reduced mass. But since the proton mass is like 1,000 times heavier than electron mass, reduced mass is approximately equal to electron mass. Therefore, we can forget about proton and we can just focus on the central potential problem. Let me just now start from the beginning. Then assume a single electron in this central potential, which is minus E squared over 4 pi epsilon naught 1 over R. So let's plug this in the radial equation we derived yesterday. What radial equation was? Minus h bar squared over 2m d squared u d r squared plus minus e squared over 4 pi epsilon naught 1 over r plus h bar squared over 2m l plus 1 over r squared. U is equal to E times U. And our job is to solve this equation. Right? Everything is given now. So this entire thing we called yesterday is V effective. So let's draw how it looks like. So this is V. So there are two contributions, right? There is like Coulomb contribution, but there is like minus, and as R goes to 0, this Coulomb is going to go like this. And the other component is like positive, right? H bar square m and L plus 1, they are all positive. This one goes like this. And what happens is if you sum these two, you are going to get something like this. Yes?
On the right-hand side of the equation, you wrote each side, or should it be EU?
Oh, yes, thank you. I appreciate, absolutely. Yes, a little bit careless. Now, so let's remember what we are trying to do. There are two kinds of problems, bound states and scattering states. And scattering states are defined by positive energies, because we are assuming at infinity the potential is 0. So if your energy is above the value of potential at infinity, we call them scattering states. So we have this continuum of So this is continuum scattering states. But also, so right, this is 0. If energy is smaller than 0, 0 is the value of potential at infinity, we have bound states. And bound states are discrete. So we have 1, 2, 3, 4, dot, dot, dot. So these are discrete bound states. And to understand the hydrogen atom, we need to solve it for bound states, because electron is bound to hydrogen atom. It's not scattering off. Right? Now we have to assume E is less than, so assume E is less than 0 in the following. Good. Now this is one of those things, right? There is like an algorithm. We are going to run the algorithm. No matter how ugly things look, right? We'll persevere. We'll be patient. But at the end, we are going to understand something we didn't know before, right? We are going to see how these energy levels come out in full solution. That's not like some Bohr semi-classical argument. We are going to solve the full wave equation. Okay. All right. So the first thing we do, so this is going to be kind of like the analytical solution we did for harmonic oscillator, but this is a little bit more complicated. And the first thing we need to do is we need to put the equation in a dimensionless form. So we also did that for a harmonic oscillator. Let me just copy this and show you how to do that. Okay. So what I will do is I'll erase this E and put E, which is just a number, which is a negative number here. And I need to put another E here and another E here. Good. Now I want to define this. You can see something in the denominator is multiplying R. This time this should be dimensionless because dimension of U on the right hand side is 1. So whatever is multiplying U on the left hand side should also be 1. Therefore I define this kappa like this. Actually kappa square like this. And because E is negative, this kappa square is positive. So there was like E here, I just took it here, and I defined this thing to be kappa squared, or 1 over kappa squared. So this is 1 over kappa squared. Then here, let's recognize the factors here. So this thing, so h bar squared, r squared, is going to be called rho squared, right? If you want this kappa times r, I define to be rho. And here I have another rho squared. You can see here. I have one more. This is also rho squared. Actually, this is minus rho squared because we define kappa with the minus sign. And lastly, so you can see I have here this factor. Let's take care of this factor separately. So I want to have rho here. And to have rho, I can multiply it with kappa and divide with kappa. Yes. And this one I am going to call E is negative, right? Minus this thing is positive. I am going to call, so this thing is, you can see rho, and this piece with including E, let me try to draw it properly. I'm going to call it rho 0. Then this equation will be a little bit nicer and a little bit palatable if you like. So this is going to be d squared u d rho squared plus rho 0 over rho plus L plus 1 divided by rho squared u is equal to u. Good. And I want to
isn't it minus rho squared?
it is not minus because there E is negative, right? I defined this entire thing to be positive. So I want to take this entire factor to this side. So what I will do is I'm going to put equality here, and I'm going to put 1 minus here and erase this. Let me check if so this is, yes, good. So this is the form. Now you can see there are only two parameters I have to keep track. There's L plus 1, and there is rho 0. And it's going to make it a little bit nicer, and it will be less likely to make mistakes. So the number 2 is check asymptotes. So rho goes to infinity, but in this case we also need to check rho goes to 0 asymptotes, so that we can parameterize this u in a nice form that's going to be convenient for this power series solution. So let's first check this rho goes to infinity. I can drop this and drop this, and equation becomes d squared u d rho squared is equal to u. And the solutions are something like a times e to the minus rho plus b times e to the plus rho, right? They both solve the equation. But this term blows up, so goes to infinity as rho goes to infinity. Then we take b is equal to 0. Okay? So as rho goes to infinity, we have exponentially decaying solutions. Now let's check rho goes to 0 limit. In that case, this term is going to dominate all the others, right? So this is d square u d rho squared is equal to L plus 1 over rho squared u. And here we can try something like this, something like a times rho to the k, and derivative is a times k rho to the k minus 1, and second derivative is a times k minus 1 rho to the k minus 2. Plug in, so I have k minus 1 a rho to the k minus 2, this is that side, is equal to L plus 1 a rho to the k divided by rho square minus 2. So this one cancel, a's cancel. So there are two possibilities. Either k is equal to L, right? Then, right, so this k is equal to L, k minus 1 is equal to, how did I do that? So either, so smaller one should be smaller one, right? So this is k is equal to k minus 1 is equal to L, k minus 1 is equal to L, then k is equal to L plus 1, or, so this is option 1, option 2 is k is equal to minus L, then k minus 1 is equal to minus L, L like this, and this is equal to L plus 1. So they both solve the condition. Then the most general solution should be something like A rho to the L plus 1 plus B rho to the minus L. But similarly, so this thing blows up as rho goes to 0, then take B is equal to 0. So we have two asymptotes. One asymptote, as rho goes to infinity, there's this exponential, and the second asymptote is rho to the L plus 1. Then a reasonable function to put in this equation before the power series is the following. So ansatz of the form u is equal to, there's this rho to the L plus 1 e to the minus rho times some other function v of rho. So this is the second step is complete. So what I will do is now I'm going to calculate second derivative of u and substitute in this equation, and I will transform this equation from u to v. And after that it is going to be ready for power series, and we are going to do power series, and we are going to try to find the spectrum. Okay, so first u prime is equal to this thing. So this is L plus 1 L plus exactly the same thing plus the same thing. So this one is minus because e to the minus 1 is like this, plus derivative of that. And I want to collect factors. So this is rho to the L e to the minus rho times I have L plus 1 minus rho multiplying v plus v prime. I think I also have rho here because I take this one out. So this is rho. So first derivative was not bad. We have to do one more. So u double prime. So I can take derivative of this or derivative of that. So let's do that. So this thing L minus 1 plus derivative of second one is going to just give me a minus like this. So this is minus, and the derivative of last one, and so like this. And now I need to take the derivative of this. So, okay, this is plus. So this one is derivative of this minus v plus L plus 1 minus rho v prime plus derivative of this is v prime plus rho times v double prime. And this is plus v plus, okay, now I can do this 2 and erase this. And I think these are all the factors I have. Good. Okay, let me collect things. So I want to write it like rho to the L e to the minus rho. So there is like a v term. So v term is L L plus 1 divided by rho, right? There's L plus 1, and I take one row inside. So this is minus 2L minus 2 plus rho. So this is the V terms I collected. Let me just copy from this, because I'm very likely to make a mistake if I do it again here. So this is 2L plus 2 minus 2 rho plus V double prime rho. Okay, this is U double prime. And U double prime is equal to, let's go back to equation, this thing. So U double prime is equal to, so this is the right hand side, and U is equal to, what did we say, rho to the L, E to the minus rho times U. Now cancel this, cancel that. So I have cancel this factor. So this is rho. Somehow, why did I miss?
I think we're missing
V prime. Oh, here, this one, right? So this is V prime. So this one is supposed to be rho squared. Oh, I see. So what I did is like, so this was plus 1. I pushed one row inside. So this is rho. So this one is gone. So this one is gone. And this, okay. So this one is going to be rho, right? Because our ansatz is L plus 1, not L. Okay, good. So now this one cancels this. So this one is rho 0. And at the end, let me just clean up. So we have rho times V double prime. So this thing is taken care. Plus all V primes are here. So I'm going to write it like 2L plus 2 minus 2 rho times V prime. So this one is gone. And is that correct? 2L plus 1. Yes, I think this is correct. And lastly, plus, I collect everything on the same side. So this is going to be rho 0. So this thing is gone. And so this, you can see, is going to cancel this. Oh yes, good. At the end, I have rho 0 minus 2L plus 1. Anything else? That's it. And this is V. Now the last step is power series, and I think I have just the right time for that. And the hope is this new form can be solved with a power series expansion, and that's what I want to do now. So let's try a power series solution. So what I mean is this V as a function of this rho, try this j is equal to 0 to infinity, rho to the j, Cj. And the goal is to find a recursion relation for the coefficient Cj, exactly like we did for harmonic oscillator in 1D. So let's try term by term. The first term is equal to rho times, I am going to take second derivative of this thing. So the first derivative times j, and second derivative times j minus 1. Okay? And there's like row, let's push this row inside. This is j minus 1. And at the end, the goal is to write everything in terms of row to the power j, so that we can combine them. Here, then I need to shift the indices. I will redefine j, right? I will just shift whenever I see j, I need to shift it by 1. So this one is going to be j. So this one is going to be j plus 1. So this is going to be j plus 1. And this one, j plus 1 minus 1, is going to be j. Okay, so we have the first term. Now I look at the second term. In the second term, I have a constant multiplying derivative of v, and I have something like rho multiplying derivative of v. And let's do them separately. So what I want to do is like 2l plus 1 v prime is equal to 2l plus 1. So again, the same function, and I'm going to take the first derivative now. So first derivative is, sorry, there is no first, yes, first derivative, j minus 1 times j. And I'm going to push this 2l plus 1 inside. So let me write it like 2l plus 1. And since the goal is to make them the same power, I need to shift the index here. And the way I do is like j goes to j plus 1, j goes to j plus 1. Here I have only one j plus 1. And that's it. Good. So I have the first term, this term, so I need to do exactly the same thing for minus rho times v prime, minus rho times v prime is equal to minus rho times this thing. I'll take the derivative, and derivative is minus 1 times j, and if I push this rho inside, so this minus 1 is gone, so no shift is required here, and this minus 1 I like writing inside so that I can see my minus signs. Yes?
Minus 2 rho.
Oh, yes, yes, minus 2 rho, yes. Minus, thank you, minus 2 rho. So this one is going to be 2 rho. Oh, rho is like there, we shift it, it was minus 1, and with it was minus 1, with multiplying with this, it is gone. There's only minus 2 here, so this is minus 2j. Good. So I got this term, I got entire first derivative term, and there's only last term. Let's also write that last term. So this is rho 0 minus 2l plus 1, this entire thing, multiplying v is equal to this thing times this entire thing. Okay. Now I can sum all of these and then say that since what multiplies rho to the j should be 0, for this equation is valid for every rho j's, then total coefficient should be 0. So what I mean is, so let's sum this, and what we find is 0, because this differential equation is equal to 0, should be equal to j is equal to 0 to infinity Cj. So when we collect Cj plus, okay, this is rho to the j. So this is rho to the j. Collect Cj plus 1 terms. And I have here j plus 1. So I got this one. And I have here plus j j plus 1 times 2l plus 1. I got this term. So there's, okay, now I can close this bracket. Plus c, actually let me write it here, plus cj so this one is minus 2j, so I got this one, and this one is plus rho 0 minus 2l plus 1. Close and close. Good. Since this equation is valid for any row, right? Row, I don't know, 0.1, 0.5, that means this entire coefficient here should be 0 for this to happen. Right? That's also the general argument. From here we find a relation between Cj plus 1 and Cj, and this is going to be 2j plus, actually let me combine, 2j plus l plus 1. So I got this, and this on the other side is going to be minus rho 0. Divide this entire thing. So I will take the j plus 1 parentheses here. So this is j plus 1. So this is j plus 2l plus 2 times cj. Check. Any questions? Now the next step is to check the asymptotes of J series, right? Because we want to make sure, like we have like an infinite series in J. As J goes to infinity, we need to have like sensible results. This is also what we did exactly in like 1D quantum harmonic oscillator. So let's check. J goes to infinity asymptotes. So Cj plus 1 as J goes to infinity is asymptotically equal to, so here these are all constants, I will only have 2j, and in the denominator I have j and j squared, and I will cancel this j squared with j, and I will have 2 over j times Cj, and that means Cj is asymptotically equal to 2 over j minus 1 times Cj minus 1, and Cj minus 1 is asymptotically equal to 2 over j minus 2 j minus 2, and this is going to be equal to 2 over j minus 3 j3, and then it will just go on until you hit C0. And this thing is asymptotically, you can see 2 to the j divided by j factorial times C0. Then now we need to put this in V of rho and see if the result is sensible. V of rho asymptotically equal to j 2 to the j over j factorial times rho to the j, but this thing is asymptotically equal to e to the 2 rho. Good. And we go back and look at our definitions. Here's the definition. Yes. But like asymptotically, j minus 1, j plus 1 doesn't matter, right? Because it is not an equality sign anyways. So that means this thing is asymptotically e to the minus rho here and plus 2 rho here. It's going to be e to the rho and this thing is going to blow up as rho goes to infinity. So because we didn't take care at the moment of j goes to infinity asymptote, rho goes to infinity asymptote also blowed up. Okay. And what was the argument? How do we prevent this from happening? So here's the series. How can I stop this?
There should be a term that equals to 0.
Exactly, right? You need to terminate this series so that it doesn't go to infinity, and then your problem is solved. So let's say this series is 0. Suppose like some maximum Jm, there's like a maximum Jm in which Jm is non-zero, then Jm plus 1 is going to be 0. That's what I require. So let's put this here. So require C Jm non-zero. So this is the maximum coefficient of the expansion, but C J maximum plus 1 to be 0. That means if I put here in that equation, whenever I see J, I need to put Jm. So this is Jm. So this is Jm. So this is Jm. And I require this to be 0. And this gives me rho 0 is equal to 2 Jm plus L plus 1. Good. Now the convention is generally to define a new integer, because this is a little bit complicated. We introduce n, which is going to be our principal quantum number, is equal to Jm plus L plus 1. And because this is the coefficient of polynomial expansion, right? N is 1, 2, 3, dot, dot, dot. So we need to start like that. And that means L can go from 0, 1, 2, dot, 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 all the way to n, because of this plus 1, n minus 1. So we'll talk about this in just a little bit, but for the moment let's play with this. So this rho 0 is equal to 2n. So this n is going to be our principal quantum number. Let's see what rho 0 was here. So I want to take these definitions. So let's take so these were the definitions that now we need to use. So this is rho 0. All right. So the goal is now to find E, and here rho 0. I have two equations, and I have rho 0 given here. To write, the goal is to write E and this kappa in terms of n. That's what we want to do. So what I do here is, so let's try rho 0 is minus E squared over 4 pi epsilon 0 kappa over E. So from here you can see, so let me use this equation. So if I take one of the kappa here, you can see kappa over E. So from here, kappa over E is equal to minus 2m over h bar squared times 1 over kappa. So then I can write this here. So this minus and this minus is going to cancel. So this is E squared over 4 pi epsilon naught 2m over h bar squared 1 over kappa. And from here I see this kappa is equal to h bar squared over 2m. I think I want to let me write here and modify, otherwise I'll miss a factor. So this is, so I want to take rho 0 to here and kappa to here. So kappa is there, rho 0 is here. This is 1 over rho 0, but rho 0 is 1 over 2n. So this is 2n. And I want to combine, so this is equal to, let's cancel this 2 with this 2. And I want to introduce so-called Bohr radius. So this is a Bohr times n, where a Bohr is 4 pi epsilon naught h bar squared over m e squared. 4 pi epsilon naught h bar squared over 4 m e squared. Yes. So this is a number with unit of length, and if you calculate, right, these are all constant. M is electron mass, or if you want reduced mass, electron charge, and all these things are going to give us something like 0.5 angstrom. So this is what kappa is. Once kappa is found, we can try to find E, right? And so this is, let me use kappa squared is equal to minus, right, from here 2m E over h bar squared, and this gives E is equal to minus h bar squared over 2m kappa squared, and we have kappa here. If we put all these numbers, let me just write what it is. E n is going to depend on n minus m over 2 h bar squared E squared over 4 pi epsilon naught squared times 1 over n squared. And this becomes, let me write it in a cleaner form. If, right, m is a number, h bar, E squared, all of these things are numbers. If you put and convert it in the electron volts, what you are going to find is this is 13.6 electron volt divided by n squared. And I remind you here, n is equal to 1, 2, 3, dot, dot, dot. Right? So this is exactly the result you get from, if you want Bohr quantization, right? In the Bohr quantization, we are saying that angular momentum is quantized, and we put it in the energy expression, and it gives us exactly this relation. But the difference here is we solved the full wave equation. All right? We have, through these complicated recursions and then all these like asymptotes and spherical harmonics, we have the full wave function. This gives us the full electron distribution. Whereas Bohr approximation does not do that. It's like so-called semi-classical method. L is going to be 0, 1, dot, 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 all the way to n minus 1. And I want to just see the spectrum pictorially because we did this last time. Let's do it again. Okay, so if you remember, we said let's solve the radial equation for the simplest system, and we said let's consider like a spherical infinite valve, and the spectrum was something like this. Let me redefine this because I'm going to use it, and I want to now use exactly this, but for this new results. So I have L. So this was the spherical box. Let's write much simpler, minus 13.6 divided by n squared. And I want to go n from 1 to, I don't know, 6. And L will go from 0 to n minus 1, right? So this is n minus 1. Okay, these are the numbers. But now I want to put this in a picture like this and see what it looks like and compare. So it is something I need to also put. Let me just try to make it a little bit nicer to look. So, and also I want to put these numbers out of my way. I think that's enough. Like I'll just copy. Okay. So it's something like that. So what is this? So this part is energy. That's our like energy level diagram. This is the spectrum of this problem. So you can see this is 13.6. So this is L is equal to 0, L is equal to 1, L is equal to 2, 3, 4, 5. And ground state, there's only one ground state, which is non-degenerate. So this was our previous problem. So if you compare, like this ground state is also non-degenerate. Now the first excited state, right, there is like L is equal to 1 and L is equal to 0 and L is equal to 1. And let's see if they are degenerate. They are degenerate, right? And we know if they are degenerate because energy does not depend on L. Whereas here, you can see L is equal to 0, right? There is no L degeneracy, right? Like if you go to first excited state, right? It's like somewhere over here. And different L's do not have the same energy. If you look at here, we can even increase that. If you look at here, different L's, again, with the given energy, there's only one L energy level. Go to here, there's like L0 here, there's no other. But here, you can see L is equal to 0 and L is equal to 1 are degenerate. And of course, each one is also like, there's also higher degeneracy because this is L is equal to 1. There's also M is equal to plus or minus 1 and 0. These actually yellow levels are fourfold degenerate. But this degeneracy is expected. This is coming from rotational symmetry. But this degeneracy is not coming from rotational symmetry. There is like a story about this. I think you can read your book. But it is like, there is like a so-called, this is, if you want, some people call it hidden symmetry, or sometimes people call this accidental degeneracy to make it sound nicer. But the story is there's additional conservation in the Coulomb potential. Right? This is special to Coulomb potential. And in the Coulomb potential, there is like so-called, what was it called, Runge lens vector, like you can look at it, Runge lens vector, which commutes with the Hamiltonian, and there is like additional conservation because of this. And this one corresponds to these orbits right? These orbits being on a plane and also being closed, like planetary orbits. If you do the Newtonian mechanics, planetary orbits are on a plane and they are closed. But they are like higher order terms, right? Like, for example, if you do the calculation general relativity, right? There's only one planet that actually deviates from this significantly. Does anybody know this? And it was actually observed like a long time ago, and people were thinking about like a new planet being out of our sight, but it turned out to be result of general relativity. Mercury, yes. So what Mercury is doing is not this closed orbit, but it's like this. So every time it just precesses a little bit, like something like that. I mean, I'm exaggerating, but it's right. It's not only changing the plane of the orbit, but also the orbit is not closed. And the reason for this is like it is not 1/r potential anymore. It's like GR potential. Similarly, here we have 1/r potential. In quantum mechanics, we also have this nice thing. Because of this, these levels are degenerate. And you can see that, right? Even though like infinite spherical well is also rotationally symmetric, it doesn't have this property because it is not as symmetric as 1/r potential. So maybe let me say a couple of more things about this. So we solved the problem, right? And there is like recursion relation. Here's the recursion. Okay, here's the recursion relation. For any given n, you can order by order solve this problem. And not to waste our time with that, let me just write the full solution and ask you to draw some pictures if you are interested. Full solution is going to be this principal quantum number, angular momentum quantum number, and this magnetic quantum number, and it's going to depend on r, theta, and phi. There is like some gigantic normalization. Let me just write it so that I know you've seen this at least once in your life. So this is factorial divided by 2n n plus L factorial. So this is the normalization constant. So there is this e to the minus rho piece, but rho is r over 2 a bar. So this is the factor coming from requirement of decaying solutions as r goes to infinity. Here is the polynomial part. So this is the piece that's required because wave function needs to vanish as r goes to 0, and it goes like L. And now there's also a polynomial part coming from the power series, and that polynomial turns out to be a special function called Laguerre function. It is like n, actually associated Laguerre function. It's like n minus L minus 1 to L plus 1 to R over n a bar. And lastly, there's the angular dependence, which we are going to understand better today and in the coming lectures, which is spherical harmonics, L, M, theta, and phi, right? I mean, you may not appreciate this, but like we don't have many exactly solvable systems. And I think it is like a gift that even for a hydrogen atom, we can exactly solve this problem. And that gift is the reason we understand, for example, the periodic table. If we didn't have this exact solution, I think it would be very, very difficult to go to more complicated systems. And these things are like normalized. For example, if you have n, L, M, inner product with n prime, L prime, M prime, these are nicely normalized and are orthogonal. N prime N, L prime L, M prime M. Maybe I can give you an exercise and let's take a break. So here's the exercise if you are interested in learning more details. So this property I told you also has in the 3D quantum harmonic oscillator. consider 3D quantum harmonic oscillator. So V of x, y, z is equal to V of r. It only depends on r, and it is given by 1/2 m omega squared r squared. So this is also a central potential. First, you can solve this. Solve in Cartesian coordinates. So E is going to have 3 indices for each direction, E and X, and Y, and Z is h bar omega. Each one comes with n plus a half. There are 3 times a half plus an X, and Y, and Z. So this is very trivial solution, and you need to like try to see degeneracies. But the difficult one, if you have the appetite to solve this, solve in spherical coordinates.
Your 3/2 is coming from degree of freedom.
Yeah, it is not degree of freedom. Each harmonic, they are like harmonic oscillator in each direction. Each comes with 1/2, n plus a half, right? H bar omega. That's why you have 3/2. And the interesting one is like solve in spherical coordinates, and verify. I'm not sure if this is correct. Verify. I found something like this. E is equal to h bar omega 3/2 plus L plus 2n. And the nice exercise to compare the degeneracies of this result with this result. And you will have to do, again, power series expansion and then asymptotes, and then terminate the power series, find the condition for that, and it's going to give you the energy, which is going to be like that. But the advantage of this thing is like you have the full spherical symmetry manifest in your hand. This one is a little bit harder to see the spherical symmetry. Good. Okay, let's take a break.